Continuing on here, chapter 2. Last time we talked about a couple things. We talked about how to take proper measurements. Remember that when you are taking measurements, it's really always important to look at the scale that you're dealing with. And really, as we talked about again, there's usually two markings that you look at. There's sort of the large markings, which do have actual numbers typically associated with them. And again, you want to kind of figure out what that represents, the difference between the large markings, which again, in this case, as we saw, was 1 centimeter. You also have small markings, usually, which are between those larger markings, which do not have any numbers usually associated with it. You want to kind of figure out what does each of those markings represent. Again, you want to start counting, as we talked about, after the last large marking and stop at the next large marking. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And again, you can just divide this by 10 if you're not sure, and that tells you each of the small markings, 0.1 centimeters. So as we talked about, one of the ways you can look at sort of the tolerance of your measurement or the uncertainty of your measurement is if you can for sure figure out what the smallest marking represents, all you have to do is basically just divide it by 2, and that will give you really how far you should take your reading to. And in this particular case, we actually can take it to 2 decimal places on the particular scale. And that means that we should always take it to 2 decimal places on this scale. Even again, as we talked about, if it's like right on a line or right on a marking, we do have to add that extra sort of zero, if you will, to sort of maintain the proper number of digits that we should have. So again, in this case, this would be 1.1, 1.2, 1.3, 1.4, 1.5. We do record all of our certain numbers whenever we take a measurement. So that's all the certain numbers, which again are pretty much any numbers that anybody that looks at it, everybody should agree. And then we have that sort of first uncertain numbers also recorded. Again, in this case, if it's right on that marking, because I have the ability for sure to take it to 2 decimal places, I do need to include a zero here, obviously with the unit. And that's my first uncertain number. And we do want to include here at this school sort of that tolerance. So plus or minus 0.05 centimeters would be how you would be expected to sort of record that measurement, especially in the laboratory as you go through. They do, again, want you to kind of include that with your measurements. Typically speaking, you can go usually one more place to the right of the smallest marking. Not in all cases, but in 99% of the time, whatever the smallest marking is, most of the time you can kind of go one more place to the right. We did see an example of that where you can't do that. But this dividing by 2 does always sort of tell you how far you should take the reading. So if you remember, maybe that scale was 10 milliliters was the large markings, and the small markings were 2 milliliters. And for example, you divide that by 2, that tells you 1 milliliter, which means you should take your reading to a whole number. So in that particular case, even when we can't go to the right of the smallest marking, just divide them by the 2, the smallest marking, it definitely will tell you sort of how far you should take your reading to. A reminder that when we do that, when we do take a measurement, that represents really significant figures. So when we take measurements, they have a certain number of significant figures. It is based on the equipment that you're using as to how many it has, and they're all important. We also talked about sig figs in general and the sort of rules. So all non-zeros, right, again, are going to be significant. So we always start counting left to right. And we really do start counting as soon as we hit the first non-zero number. That's sort of where we start. And that will give us our number of significant figures. When we have zeros, that's some problematic for people. There's those leading zeros, which are not significant. So again, you could have as many zeros as you want before you hit that first number. None of these are going to be significant. Again, it's not significant figure until we start counting right there at the 4. And in this particular case, we will end up with obviously all three of these being significant, and we would have three significant figures in this case. We have trapped zeros, which are zeros that are significant. They are trapped between two non-zero numbers. So if we have, again, 4001, we start counting here, which is significant. These zeros are trapped, which make them significant, and that is obviously significant as well. So this would be four significant figures. And we have trailing zeros, which may or may not be significant. And it really has to determine what is significant is there is a decimal point in the number. So if there's a decimal point, then they will become significant. It does has to be written. It can't just be assumed to be there. So it has to be actually written in the number. So if you had 0.0420, these are not significant, 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 and significant here because the decimal point is there. So this guy would have three significant figures. Any questions on any of that stuff there? All right. We also talked about, again, a couple of things. Obviously, measurements have a specific number of significant figures, and those are what are obviously considered measured values. We also talked about last time exact numbers there towards the end. Exact numbers are, again, pretty much in chemistry sort of determined by two sort of things. They are things that are either counted, so you got something, you're just going to kind of count it like I think the eraser example, you're not going to do any type of measurement to try to figure out how many erasers you have. And there are definitions, like 1 inch is 2.54 centimeters exactly, 1 pound is 453.6 grams, 12 inches in a foot, 3 feet in a yard, 1 mile is 1.609 kilometers. So here, these are some exact numbers that they do want you to know. So make sure that you do know these. Um, Again, the deal with exact numbers is because they can have pretty much unlimited number of significant figures. We really don't worry about them when we are sort of doing calculations because they can have as many significant figures as you want. Thank you. But we do come across them a lot, and as we've talked about, there's two different sort of units of that we come across, either English or metric. And definitely, if you're kind of doing an English to English sort of conversion, that again is considered an exact number. If you're doing a metric to metric, it's also considered an exact number. As we'll see a little bit later on, if you do kind of cross over English to metric, you usually do have to look at the significant figures, except for a couple that are up here on this particular list. Any questions on that there? So we want to round each of these to two significant figures. So let's take a look here. So when we do look at this, our second significant figure is right here at the 5. That means we also talked about rounding. So we do want to kind of look at the next number that obviously is above 5. So we are going to round up. And this would then become 36 meters, which would give us two significant figures in this case. Here we want to look at the second significant figure. Again, that is going to put us on the next one at the 8. We do look next to it, which is the 2. And in this case, we do not round up. We typically drop the numbers, but we cannot drop all the numbers in this case, right? Because if I write 38 grams, is that the correct way to get to two significant figures? It is not, because again, we have two significant figures, but the problem is, again, we have definitely changed the meaning of that number. So 3,800 and 38 are definitely two very different numbers. So, and again, in situations like this, as we also talked about last time, you don't want to do any kind of weird rounding and just drop numbers. So in this case, we do have to keep a couple of zeros, right, to maintain really what the value is. So 3,800, 3,826, basically the same value of the meaning. And it does have two significant figures. Would it be okay if I wrote 3800 dot grams in this case? It would not, right? Because now how many significant figures would I have? I would have four, right? So I can't do that. So we do want to be careful not to put decimals in where we don't really want them. We could also have done scientific notation, right? We could have done 3.8 times 10 to the 3 grams. Remember that when we do write in scientific notation, any of the numbers that come before the times 10 part are significant. So that's another option you could do. You could kind of control the number of significant figures in scientific notation. Questions on that one there. So that was also another important thing we talked about last time. We definitely don't want to do any kind of extreme rounding. Looking for our second significant figure will actually take us to the 6 in this case. Remember that none of the zeros there before are significant. We will look at the next one, and in this case, we will end up with 0.0026. These we don't have to worry about. Would I want to put those as zeros at the end in this case? So much like above, if I actually did put the zeros, I would now end up with 4 significant figures, right? And not 2. So in this case, we don't want to put the zeros because there is a decimal point here. And again, if I put those zeros in, I am now at 4 significant figures, which is more than I want in this particular case. Lastly, here, we're going to go here, going to look here, going to do a little rounding up to 1.3 kilograms. Any questions on any of that there? So now let's talk about sort of how you do significant figures in calculations. So remember that whenever you do any type of calculation, you definitely want to make sure that you give the answer to the correct number of significant figures. Now, pretty much your calculation is going to be only as good as your worst measurement. So whatever one's your worst measurement, it's pretty much going to determine how many significant figures you will have usually in your calculation. Kind of like that old saying, right? You're only as strong as your weakest link, so your worst sort of measurement is as good as your whole calculation could be. So there's really sort of two sort of processes we kind of do. We oftentimes will multiply or divide, or we will add and subtract. And multiplying and dividing works the same way. So if you multiply or divide, your answer will have the same number of significant figures as the one with the least number of significant figures. So if you add or if you multiply or divide, your answer again should pretty much be the same as the number with the least number of significant figures. So if you were multiplying 4.20 times 1.2 and you were looking for your answer, this number here has 3 significant figures. This number here has 2 significant figures. That means when you give your answer should end up at 2 significant figures. So it's always determined on the one that is the least when you're multiplying or dividing. The other sort of operations that are kind of together are adding and subtracting. And when we add and subtract, it's actually a little bit different. We actually look at decimal places rather than significant figures. So it's the least number of decimal places, not significant figures. So your answer should have the same number of decimal places as the number with the least number of decimal places. So if you're taking 1.25 and you're adding it to 3.2, write that there. When we add this together, give it the old, let's try here without the calculator, something like that, 4.45. Here we are looking at decimal places. So this has 2 decimal places. This has 1 decimal place. That means our answer actually should end up with 1 decimal place. And we should round up because that's a 5. So our correct answer here should be 4.5. Now, that does have 1 decimal place. How many significant figures does it have? That's 2. And that's really important to keep in mind because if I then took that number and was going to use it to multiply or divide, I need to look again at significant figures, not decimal places. So you want to kind of keep that in straight in your head so that you know what's going on. Any questions on that? Now, if you're doing some type of multiple steps, you do have to just kind of keep track of your significant figures. So, a couple of rules that we maybe talked a little bit about last time that just to reiterate here, it is really important to sort of keep track of your significant figures as you're doing your calculations. I again would not do a lot of rounding, especially if you're going to do a calculation where you're going to kind of continue on with those numbers and do some more calculations until the very end. So I would keep a few extra digits. Sometimes people call it a guard digit. Some people you'll see them kind of write a number down and they'll keep a couple of extra digits, but kind of put like a little line above a number just to remind them where the significant figures should be and stuff like that. You could do that. I would say again, let's keep the digits as you go through the calculation is really important so you don't get any rounding errors. At the end, you definitely should clean it up to the right number of significant figures when it's all said and done. Now, if you're again doing some multiple steps, like if you had 3.25 times 0.046678, and you're going to divide it by 1.2. In this particular case, we would follow the normal rules of sort of math, right? So normally we would do whatever's in the parentheses first, right? So that is multiplying. So here we're going to look at significant figures. So we're going to go with 3 significant figures for this one. This one's got more than that, 5. So technically speaking, when we're done, the top number should really have 3 significant figures. Now, we're then going to take that top number and divide it by the bottom, which has 2 significant figures, which means at the end we're going to take 3 significant figures divided by 2 significant figures. That means that my answer should end up with 2 significant figures when it's all said and done. Now, would I round on this? I probably want to do, again, too much rounding. I would take 3.25. I would times it by 0.046678. And honestly, on your calculator up there on top, 0.151735 is what you would get. I would at least write all that. If you don't want to write all that, I would cut it down a little bit. But definitely, I know it should be 3 significant figures, which is here. So again, I would probably at least take it out to here just to have a couple of extra digits. To be honest with you, on my calculator, I would just use the whole number, not like, round it off in my calculator, just use the whole number I got on that first part of it and hit divide by the bottom there, 1.2. I guess that's not really 5, 1.2. And we would end up on my calculator at this point 0.126419583. At this point, again, I would kind of keep track of everything and know that I should end up right here, which is 2 significant figures. And now I should end up at 0.13. Okay, so I would definitely keep track of significant figures. And again, some people do something like that, kind of put a little line over where the significant figure should be or where you should round that to. But you definitely don't want to take it all the way down probably till the end. Keep a couple extra digits in terms of rounding error. On that push. A reminder again that calculator will not give you the proper numbers. Usually, maybe I get it, but it's not going to give you the right number of pigs or anything like that. So just make sure you track it. All right, so for each of these examples, this is again, calculator gives you, round them off to the proper number of digits. So take a few moments there and see what. Okay, so let's take a look. So first one here, we are multiplying. So again, we're looking at significant figures. So we got 3 sig figs there. We got 2 sig figs there. That means that we should end up at 2 significant figures, which is right about there. Again, looking to the number to the right there, which is a 7, we're going to round up. Looks like a 9.4 there for the first one. Any questions on that? Next, we are dividing. So again, we're looking at significant figures. So that is 4 significant figures. That is 3 significant figures. That means 3 significant figures is what we're looking at, which would take us to the 8, We look at the number next to it, which is a 2, so we're just going to drop them here, and we will end up with 0.0758. Once again, we cannot put the zeros in at the end, otherwise we have too many significant figures. Next, we are adding, so we are looking at decimal places, not significant figures. So 2, 1, 3, and 3. So that looks like one. That's the answer, actually. So one decimal place is the smallest, so we actually will come out to one decimal place there, and we'll drop the rest, so 29.1. Lastly, decimal places here on subtracting, so that's 4 decimal places. 1 decimal place should take us to 1 decimal place. That will give us 0.6. Once again, it has 1 decimal place and 1 significant figure in this particular case. Any questions on that? Now, what happens if I'm adding something like this, like 12 plus 1.22, and I get 13.22? This should be to what? Smallest number of decimal places is none, right? There's no decimal places on the first round. So that means you should go to a whole number in this case, yeah? So if you do have a whole number, obviously it has no decimal places. All right, so continuing on here, we talked about some of those prefixes. Again, you pretty much do need to know these as we talked about earlier. And a reminder, proper use of these things. When you see something like kilo 10 to the 3, how much into the base to 1 prefix unit. So 1 kilometer, which is a prefix unit, would have 10 to the 3 meters. 10 to the 3 written like that is 1 times 10 to the 3 on calculator, scientific notation, basically. So if you need to enter that in calculator, you would enter it just like you're doing scientific notation, like we talked about earlier. 1, your exponent button, and 3. Yeah, so that would leave it. And again, it doesn't matter the units. It works the same way. So if our base unit here are grams, 1 kilogram would be 10 to the 3 grams. All right, so some of these common measuring lengths that we talked about are qualities. 1 meter is 100 centimeters, 1 meter is 1,000 millimeters, and 1 centimeter is 10 millimeters. These are, again, definitely all ones that you should know. Volumes, 1 liter is 10 deciliters. 1 liter is 1,000 milliliters. Again, I would say probably most of the time you're definitely going to see that one. You should maybe have an understanding of the others, but most of the time you would definitely see that 1 liter is 1,000 milliliters conversion used a lot. We also talked about, I think earlier on, just a reminder that if you take 3 length measurements of something like a cube, it will give you the volume of it, and that is in cubic centimeters. So 1 milliliter is equal to 1 cubic centimeters. Again, that is a volume, and it's achieved usually by taking the length times the width times the height. Each of these in a length measurement like centimeters gives you cubic centimeters, which once again is a volume. Each of these individual ones are length measurements, distance measurements. And as we saw earlier there, cubic decimeters is a liter. And we talked about, again, looking at our scaling and making sure a lot of times when we do take a volume reading, especially in the glass container, that we do look for the meniscus, which is usually in that U-shaped sort of fashion. And again, we always want to read from the bottom of the meniscus when we're taking a reading. Once again, if you look at something like this scaling here, our large markings, right, is 10 milliliters, difference between those. Small markings, we have 1, 2, 3, 4, 5. That means that each of our small markings in this case is 2 milliliters. That means the best we could do if we divide that by 2 is plus or minus 1 milliliter. So if we were using this particular piece of glassware with this particular scaling, the best if we take a measurement is to the whole number. So remember that that's on the piece of glassware. and or you can't take that reading. Definitely, I would say probably these all are good ones to know. Kilograms, 1,000 grams, grams, 1,000 milligrams, and this is micrograms. That's micrograms. Well, I skipped through those, I think. All right, then let's talk a little bit about writing conversion factors. That's the one I think the other day. But when we have these equalities, we could really write a conversion factor. And again, it'll be two values which are on different scales, but do represent the same amount of something. So again, if you have 12 inches equals 1 foot, that is an equality. They both represent the same amount of distance or length. And from any equality, you basically write two conversion factors from them. And they're basically just fractions. You could go 12 inches over 1 foot or 1 foot over 12 inches. The reason we do this is something else we kind of touched upon earlier on in this chapter. The way that we show work, the way that we show our calculations is through dimensional analysis. And again, dimensional analysis is that idea that we talked about earlier, where we take a unit that we do not want and we use a conversion factor to get rid of it by putting that same unit in the opposite location. So again, if we have just one unit by itself, we assume it's up on top. We use a conversion factor here to get rid of it in the opposite location. And whenever we do dimensional analysis or set it up like this, we always know the math that we're doing. Anything on top gets multiplied. Anything on the bottom gets divided. And by doing so, unit A on top will cancel out unit A on the bottom. Again, it's the same idea. If you took 2 divided by 2, same on top and bottom gives you 1. Same unit on top, same unit on the bottom will cancel out and become 1 and get rid of itself. And you will end up with the unit that you want here. Now, for any equality, you could write two conversion factors. Will you use both of them in the calculation? I hope not. Otherwise, you're going to probably undo your calculation. You're going to choose one to use. And it really is that simple of, I have this unit up on top. I need it on the bottom. So whichever conversion factor has it on the bottom, this is what I want. Or vice versa. If I have the unit I want to get rid of on the bottom, I need to have that same unit up on top. So it makes it easy to choose your conversion factor. Any questions on that there? Again, a common sort of conversion, $1 is equal to 100 pennies. Again, that's an equality. And it represents the same amount of money, right? You could go somewhere and pay with pennies. You could go somewhere and pay with dollars. If you have 100 pennies, same as if you had $1. And again, you can get two conversion factors from that. 100 pennies over $1. Or you could flip it around and do $1 over 100 pennies. So again, these are sort of the two conversion factors available to you. Depending on what conversion you need is really the problem. So again, if I had $5 and I want to know how many pennies that was, dollars here would be up on top. That means I need it in the opposite location. So I would use it like so. 100 pennies up on top, $1 on the bottom. I'm going to multiply and then divide. The lowers will cancel. 5 times 100 is 500 pennies, right? And again here, in terms of significant, that's one thing about dimensional analysis is the type of math that you do in it is multiplying and dividing, which means you're always looking at significant figures. Because the 100 pennies is $1 is an exact number, it's a conversion. We don't even bother with looking at it. So we would just look at our original number, which was 5, which has one significant figure. And then 500, like I wrote it, is one significant figure. So that's the only thing that we'll look at really in terms of sig figs was this original number. Here are some common equalities. And we have US metric and kind of crossing over. This is probably just a really good chart to know as you go through your chemistry career here. But we have US to US sort of conversions. 1 foot is 12 inches, 3 feet in a yard, 5,280 feet in a mile. I say all those things pop up a lot. 4 cups is a quart, 2 pints is a quart as well, 4 quarts in a gallon. Definitely our metric ones, pretty much the entire columns in there. We've come across a lot of those, and we talked about some of those, obviously, as we've gone through earlier. A lot. And then we have our metric to US. So some of these, again, are considered exact. And here, again, these are considered an exact conversion. Here, they kind of consider this one an exact conversion. Maybe not everywhere else, but here. So those are exact conversions. So let's talk about sort of significant figures if we're using any of these sort of equalities. If you're using any of these equalities, that's again sort of in this column or any other one that sort of would be in this column, a US to US conversion, you do not have to worry about a significant figures. They're considered exact numbers. So if you're doing a calculation with it, you don't really have to worry about the actual conversion factor and its significant figures. So these would all be considered exact. Same thing here. Anything that would fall sort of in a metric to metric conversion would also be considered an exact. So if you're using 1 kilometer is 1,000 milliliters, you don't have to worry about significant figures in that conversion factor. You just kind of ignore it when you're doing your calculation. The only place where you really do have to worry about it is here. So here you do need to look at the sig figs typically. If you're doing any type of metric English sort of conversion, the only ones you don't have to are there's a couple there that are listed as exact. So the 1 inch is 2.54 centimeters, or the 1 pound is 453.6 grams. So if you have those, you don't have to worry about it. But if you have anything, for example, if you had the 1 quart is equal to 946 milliliters. Here, if we were going to use this as a conversion factor, we would have 1 quart over 946 milliliters, or 946 milliliters over 1 quart. So if I was doing a conversion where I had 2 quarts and I want to know how many milliliters that was, actually I'll do 2.0. We'll do 2.0 quarts. I would set my problem up like so, 2.0 quarts, again, doing dimensional analysis. If it helps you, you can put that over 1 and see that the quarts are up on top. That means I would need to use this over here. 946 milliliters is 1 quart. Again, we're going to multiply the top, divide the bottom. The quarts will cancel. That will give us, if we put it into our calculator here, 2 times 946. It's going to give us on our sort of screen there, 1892, I think. So now when we do this, we do significant figure. And when we look at the significant figures, we do look at the conversion factor for significant figures. And in this case, there's usually a situation where one of the numbers in a lot of cases is a 1 and the other one's an actual number. And that is the number of significant figures you would look at. So this would be rolling with 3 significant figures based off of the 946. We obviously would not worry about this number down here. We'd actually worry about that part of the conversion. We would also look at our original number here, which has 2 significant figures. And since we are multiplying and dividing, we are looking at the least number of significant figures, which means in this case, it actually should end up at 2, which would take us to here. And that would take us to 1900 milliliters as our answer. So the only time when you're using sort of conversion factor or an equality that you really have to still kind of worry about significant figure in the factor equality is if it's sort of a metric to US sort of crossover conversion. Other than that, if it's a US to US, you're good. You can ignore it. If it's a metric to metric, you can just ignore it. But again, crossover, except for those few that are exact, you do have to kind of look at it. And you want to look at whichever one is the actual number and not the 1 part of it. push. All right, so this inequality, again, 5,280 feet is 1 mile. Again, we could write two conversion factors for this. They are, once again, just uh, fractions here. So 5,280 feet over a mile. Mile is 5,280 feet on the bottom. Once again, whichever one you're going to choose will be determined by the problem that you're doing. So if you had miles and wanted feet, you would actually start with your miles, which would be up on top, which means you would want to use the miles of the opposite location if we were going to actually solve this problem. Now, if you're driving your car 65 miles per hour, sometimes you're given conversion factors within a problem. And so maybe they may be in words. So if you have something like this, 65 miles per hour, something per something is a fraction. So that means you could actually go 65 miles in 1 hour if you maintain that rate, right? Or in 1 hour, you can drive 65 miles. These are conversion factors that you could use. That is the other place where you usually do have to look at significant figure if you're using a conversion factor, and that is if you're given something in a problem that basically is not like a standard conversion. Not always are we driving 65 miles per hour, right? So if we were given that information in a problem, you would want to look at the 65 significant figures here, which would have two significant figures again, because if I was driving 125 miles an hour, that would be three significant. And I'm going kind of fast, I imagine, in that case. So another place where you do have to be concerned about significant figures is if it's given something in the problem kind of specific to that problem. Okay. So if we have a gallon of gas is $3.05 per gallon, that means 1 gallon will it costs us $3.05. Our $3.05 will cost us 1 gallon. A very, very common thing that we kind of turn into conversion factors is not fractions, but percentages. And a lot of times in chemistry, we are given percentages. And as you may know, one of the easiest ways to convert a percentage into a usable number, if you have 100 of something, right? If you have 100 of something, the percentage will basically say the same number when you convert it into a conversion factor. So if you got 85% on your exam, you probably got 85 points out of 100, right? So you just keep it the same sort of number. So for example, here, if we had something uh, or something that was 12% body fat by mass. That basically means in 12 kilograms of body fat, there are in 100 kilograms of body mass. In case you're metric, that would give us two sort of conversion factors. 12 kilograms over 100 kilograms of body mass or 100 kilograms of body mass over 12 kilograms. Doesn't matter what units, it doesn't. If you want to do more of an English like we do around here, pounds, that would mean that you have 12 pounds of body fat for 100 pounds of mass, or vice versa. 100 pounds of body mass will give you 12 pounds of body fat. Typically, we assume 100 because really, again, it just keeps the number the same. You can assume any number you want, but the numbers would change and make it difficult. So as I mentioned before, when it says show your work, when it says show your work with dimensional analysis, or even if it doesn't say show it with dimensional analysis, it just says show your work. That is really what they want you to do. So as we've been talking about, as we've seen, it really is just using these conversion factors, keeping the units sort of opposite locations will cancel. And again, you can just kind of continue on. If you started with a particular unit you don't want, you again could use a conversion factor to get you to a different unit. And let's just say maybe you didn't want to really get to that unit, but you want to get to a different one. You can just continue on. So these guys would cancel. I know this guy is up on top, which means I would need this guy on the bottom to cancel. Now this guy cancels. And you really can just continue on with that process. And again, this is the way that you should show work. These all obviously should have units and numbers associated with it. And once again, everything up on top gets multiplied, everything on the bottom gets divided. So the math is easy. Now, when you do punch something like this in your calculator, you do want to be careful, and this is where people kind of screw up a lot when they're doing this, is they want to try to type everything into their calculator all at once. And if you're not super careful and use parentheses correctly, you will end up with the wrong answer. So a really good piece of advice is to use the equal button a lot when you're punching things into your calculator. So if you had to multiply everything that's up on top, you could take as many numbers as you may have on top and put them all in at once. At the very end of that, you should hit equals on your calculator. Then you have a couple of numbers on the bottom that you need to multiply by. You should then, or divide by, you should divide by the first number and then hit equals. And then divide by the second number and hit equals again. And kind of do them individually on the bottom, and you will always get the right answer. Again, if you try to punch them all in at once and you don't do it correctly, your calculator will do the math wrong, and you will end up with the wrong answer. So don't be afraid if you have a lot of numbers on the bottom. Use that equal sign a lot in between. Just divide by each one individually, and you'll be in good shape. So let's talk a little about the steps to solving dimensional analysis problem. A lot of times it's really helpful to write what's given to you. You want to write what you're looking to find. You want to write any appropriate equalities that will get you there. Now, when you're doing just straight up conversion problems, there are multiple ways you could get to the same answer depending on sort of what conversion path you take. But if you choose anything that's a legitimate conversion, it should all get you to the same spot at the end. You want to set up the appropriate conversion factor, set up the problem showing the units canceling out, and you should solve the problem to the proper number of significant figures. So again, just take a look at a pretty straightforward one like we did earlier. How many pennies are in $3? So obviously we want to think about equalities. We want to go from dollars to pennies. And obviously here, that's going to give us our $1 is 100 pennies conversion. And that will give us our equality that we could use. Going to give us our two possible conversion factors, $1 over 100 pennies, or 100 pennies over $1. Obviously here, starting with what was given to us, which is $1, we want to go opposite. So once again, if it helps you just visualize it, you can put a 1 over it. You don't have to, obviously. And again, that just simply tells us dollars are on top. I want to get rid of dollars. Opposites cancel, so that is the conversion factor I want to use. So once again, 100 pennies, $1. All I have to remember is anything on top gets multiplied, anything on the bottom gets divided. So that is going to cancel out the dollars, and we're going to end up with 300 pennies in this case. And in terms of significant figures, we don't have to worry about that. That's an exact conversion. The only one we have here really is one significant figure. So one sig fig here, once again, will be appropriate. Any questions on that there? All right, let's take a look at some other ones here. All right, so why don't you try one here? You go to the local AMPM, get yourself 32 fluid ounces of Diet Coke from the Thirst Oasis. How many gallons of Diet Coke did you drink? Again, I'll give you some equalities that might be helpful here. So take a moment here, set it up using dimensional analysis, showing the units, the conversion factors, and see what you get. We definitely have fluid ounces. We could take fluid ounces to quarts and then take our quarts to gallons is sort of our pathway there. These are some equalities that you could get. From there, once again, you could get a choice of really 4 conversion factors to use. You're not going to, obviously, again, use them all in this problem. These are what's sort of available to you. Here we would start with our first number there, which is 32 fluid ounces. Once again, that is up on top, which makes the choice of conversion factor pretty easy for me. I want to go with that one there. So that's going to be 32 fluid ounces is 1 quart. Once again, opposite locations cancel. We are multiplying the top here, dividing the bottom. At this point, the fluid ounces would cancel out. By setting it up like this, we can clearly see the only unit left is what unit is quartz, and it also is up on top, right? Which makes a brain decision for the next one. I want to get rid of quartz, and it's on top. And I definitely need to use quartz on the bottom, opposite location, and that fine here. You could technically get an answer at this point, but you could also just continue on with the calculation. We're going to go with our 4 quarts on the bottom, our 1 gallon. Once again, still multiplying the top, dividing the bottom. By dividing the bottom there, the quarts are going to cancel, and that is going to give me only gallons left as my unit, which is what I'm looking for. I'm going to multiply across there. That's 32 times 1 is 32. I'm going to divide by the first number here and hit equals. And I'm going to divide by the next number here and hit equals. And that is going to give me 0.25 gallons. It does not give me 1 over 4, by the way, because that makes me think you're just too lazy to divide out the number. Yeah, so don't ever give an answer as a fraction. Give it out. Too lazy to actually punch a number in the calculator. That, and I've had people write something like the answer is 425 miles, 3,280 hours. Looks good. Looks like an X. Yes, so don't leave an answer in a fraction. Divide it out. First off, any question on the setup there? That is what we're looking for in terms of dimensional analysis. What's on the bottom, that is how you're expected to show your work. Yes, so when it says show your work, that is what it expects you to do. Now, let's talk significant figures, right? So here, that's considered an exact conversion, so we don't have to worry about it. That's considered an exact conversion, so we really don't have to worry about it. That means really the only number that we have to worry about in this particular case, which, by the way, in a lot of cases is probably the number most of the time you're going to look at, is that first number. Not always, but a lot of cases it is that first number. This has two significant figures, which means my answer here will have two significant figures. So, any questions on that? What do you need to show to get full credit? You need to show to get full credit what's on the bottom here. Yes. If it helps you to show everything else above it, go for it. But you don't have to do an exam or quiz kind of show above it. But to get full credit for work, what's highlighted there on the bottom, the dimensional analysis setup, also with units throughout the calculation, right? Proper sig figs at the end. That is what you need to show. Any questions on that? All right. So why don't you try this one here? An antibiotic is doses of 500 milligrams is ordered. If it is supplied in 250 milligrams per 5 milliliters, how many milliliters would you be given? Okay, so let's take a look. So here, information given to us, obviously given here a couple pieces of information. We have 500 milligrams is our ordered dosage. We actually have a conversion factor that is given to us here in the actual problem. So again, a lot of times you will have sort of conversion factors given to you in that problem, which means we can use it like I wrote it there. We could also, if we needed to, we could also flip this sort of conversion factor over and use it in this fashion. So in this particular case, we're looking for how many milliliters. So we want a way to go, obviously, from milligrams to milliliters. And it is this conversion factor here that was given to us in the problem that's going to allow us to actually do that. So we could start our problem here, take our 500 milligrams. Once again, think of it like a fraction. So that's up on top. Once again, makes it super easy to determine what conversion factor I want to use. Opposites cancel. So 500 milligrams on top, milligrams on the bottom is going to work there. So we actually do need to flip it around and use it in this fashion. We again are going to multiply the top, divide the bottom. By doing so, the milligrams are going to cancel. That will leave us only milliliters left. And we'll do a little multiplying the top there. So 500 times 5, hit equals. Divide by 250, hit equals. That is going to give us 10 milliliters in this particular case. Now let's talk a little bit here about sig figs. But first off, any questions on the calculation? Yeah. You can reduce the conversion factor down if you can. It will come out the same, obviously mathematically. I would probably recommend in our application just to use it how it's written in the problem, but obviously it'll give you the same sort of thing. Like if you had something that was like a 4-to-2 ratio, right? It's the same as a 1-to-2, right? So it will come out the same. So you're using kind of the same numbers in the problem. It's probably a good idea maybe not to do that so much, but it will come out the same. Yeah. You should definitely kind of, if you were going to do that, you should then write sort of an appropriate conversion factor that shows that. Yeah. Yeah. Okay. Yep. Other questions? All right, so we got 10 on our calculator, right, as our answer. Obviously, it may not always be the right sig figs. Here, we do need to actually look at this conversion factor because it's not a like exact conversion, right? It's kind of specific for this particular problem. Just happens to be how the medication is given to you. In this case, we actually do have two numbers given to us. We have the one on the bottom, which we do have to look at, which has two significant figures. One on top actually has two significant figures in this case because it is not reduced down, as was just sort of the question. And here, this one actually has three significant figures, right? Because there is a decimal point there, which means the zeros are significant. So since we're only multiplying and dividing here, the smallest is actually 2, which means, is it okay the way I wrote it? Will that give me two significant figures? It will not because there is no decimal point written, right? So actually the way I wrote it right now, it only has 1. I would actually need to put a decimal point in there, right? To now give it two significant figures. I can't do this, right? Because it will now have three significant figures, right? With that. So here you would have to give a decimal point at the end, or you would have to do a little scientific notation, right? And you could do it like that as well. So remember, again, not always to write sig figs on your calculator, and we do want to kind of. So in this particular case, because our conversion, once again, not an exact conversion, we do have to kind of look at the significant figures in that. When it is anything of that metric to metric or English to English, we don't have to worry about it. Any questions on that? All right, so why don't you give this one a go? I'll give you some equalities, maybe that will be helpful. During surgery, a patient receives 5 pints of plasma. How many milliliters of plasma were given? 1 quart is 2 pints, and 1 quart is 946 milliliters, which does pop up a lot, yes. All right, so set it up, dimensional analysis, see what you come up with. In terms of your answer, proper sig figs, all that good chemistry-like stuff. Okay, so once again, we want to think about a pathway to get from pints to milliliters. So basically, we have pints. We want to end up at milliliters. One way we could do that, obviously, is through here to go to quarts and then quarts to milliliters. So we could kind of use our quarts as our middle sort of pathway to get there. Obviously, from each of these equalities, we could have two conversion factors that are sort of available to us as we've been talking about. And again, we're going to start with what was given, which was our 5 pints. Once again, if you helps you, you could kind of think of it like a fraction. So that shows us pints are on top, and we want to definitely get rid of it. Opposite cancels, so makes my decision pretty straightforward here. That's the one that has pints in the bottom location. That is the one I definitely want to use, right? Don't overcomplicate things, right? And once again, here we are multiplying the top, dividing the bottom. If I were to stop right at this point in the calculation, I would be in the units of quart, right? And that's close to what I want, but I do want to get it to milliliters. Again, by setting up like this, there should be no misunderstanding. I could clearly see quarts are up on top, which again tells me to get rid of them opposite location, and that is the conversion factor I need to use, right? So we're going to set it up. And we're going to do 1 quart, 946 milliliters. We're going to continue our pattern of multiplying the top and dividing the bottom as we go across. That's going to cancel out the quarts. We're going to grab our handy dandy calculator, do a little 5 times a 946. We're going to hit equals. We're going to divide by the first number 2 and hit equals. You can divide by the second number, but it's a 1, so it won't do much. On my calculator, I now have staring at me 2365. I know my units are milliliters at this point. First off, any questions on the setup? Here we want to look at significant figures, right? So we take a look here. That is a metric to English conversion, which means we do need to look at the significant figures here. So this has 3 significant figures based off of this number. This one we do not need to worry about. We do need to worry about our original number as well, which is 2 significant figures. Again, we're always multiplying and dividing here, which means we're always looking at significant figures. And that means the smallest looks like 2 significant figures, which means we should go here, and that should end up at 2,400 milliliters. Or once again, you can scientific notation at 2.4 times 10, 1, 2, 3 milliliters. Why did I drop off the zeros when I wrote in scientific notation? Why did I not write 2.400 times 10 to the 3? If I wrote this 2.400 times 10 to the 3, how many significant figures would that have? 4, because remember, written in scientific notation, anything comes before. So here we do, if we do choose the scientific notation part, got to drop those zeros. Otherwise, we now put too many significant figures into our answer. Any questions on that there? Let's try another one here. Why not? You are stranded 125 miles away from home. You got no money. You decide it looks like a nice day. Let's take a nice walk. You walk an average of 55 feet per minute. How many days would it take you to get home? Give it a go. See how many steps you're going to get in today. All right. There's some conversion factors. Hopefully some of those you know. By the way, at some point you should know all of those that are up there, right? Okay, so let's take a look at this one. We want to go 125 miles. We're walking at 55 feet per minute, and we want to know how many days. So we basically want to go from miles to days. Those are 2 different types of units, right? So that's basically a length or a distance, and where we want to end up in time. What's going to allow us to do that is actually what was given to us in the problem, which is a conversion factor that we are moving at 55 feet per minute. That is like a rate, right? Is your distance over time. So that's what's gonna allow us to basically get from length or distance into the units of time. We could definitely use this as a conversion factor. So if we needed to, we could flip it around and do a minute is 55 feet, right? So another problem, which is our distance here is in miles, but our kind of distance or length unit here is in feet, which does require us to do some type of conversion in order to use them together. So we can't use them in miles and feet together. So you can either convert the miles to the feet or the feet to the miles, but they do have to be kind of in the same unit. I'm going to choose to convert the miles into feet. So I'm going to do 125 miles. And once again, I'm going to use this for my conversion factor. Opposites cancel, which means miles are up on top. So I do need miles on the bottom and 5,280 feet up on top. Multiplying the top, dividing the bottom, the miles will cancel. And I'm going to take basically 125 and times it by 5,280. Going to give me 660,000 feet. Definitely getting my steps in today. All right, so 660,000 feet happening here. Now that I have my distance in feet, that opens up the conversion factor that was given to us because they are in feet as well. So we could take our number, 660,000 feet. Once again, that is up on top, which means to cancel it, we do want to use the conversion factor in the opposite location, which means 1 minute will give me 55 feet. We're going to multiply the top, divide the bottom, feet are going to cancel. And again, at this point, we have now gone from really distance to time, right? We're in units of time, which is minutes in this case. That is not the unit of time we're looking for. We are looking for days, so we need now take minutes to hours, hours to days. So once again, using my next equality here, which is minutes to hours, minutes are up on top, so I need minutes on the bottom, and hours up on top. Again, multiplying, dividing, minutes will cancel. If I laid up the calculation right here, I'm at hours, which is close to what I want, but I do want days. So I could use my last equality here. Again, setting up like this, I could clearly see hours are up on top, so opposites to cancel. 24 hours on the bottom, 1 day on top, multiplying, dividing. Hours will cancel. That is going to leave me days left up on top, which is what I want. That typically is what you want if you're looking for an answer that has 1 unit. That unit needs to end up on top by itself, yeah? So that is the right way to do it. First off, any questions on the setup there? Now, if I do that little multiplication there, there's really nothing to multiply on top. Everything's a 1. So obviously we're going to get 660,000. Here we want to divide by 55, hit equals. Then divide by 60, hit equals. Then divide by 24, hit equals. And you will get the right answer. So again, divide equals, divide equals, and divide equals. Yeah. Don't be afraid to do that enough times so you don't get the wrong answer. On your calculator, you're going to see 8.33333 days. You probably won't see the days, obviously. So here we want to look at our significant figures. That obviously is an exact conversion. We don't have to worry about it. That's an exact conversion. We don't have to worry about it. This came from the problem, which means we do need to look at it. So we're going to look at the 55 here. It is written 55.0, which is 3 significant figures. And we do want to look at our original number. Do I want to look at the 660,000 number? I actually don't. I want to look at this number back here, which means that is 3 significant figures. Which means technically, even though I wrote it like this, that has 2 significant figures, this guy should have 3 significant figures from way back there. And so should this guy. Which means we should end up with 3 significant figures, which would put us at 8.33 days. It's a lot of days. Yes. Yeah. No, you're good. Yeah. So for your final answer, you mean? For the very final answer, 8.33, all good. Yeah. Other questions? So this is really important, this setup. It's really important to understand opposites cancel. I can't tell you how many people would do this problem and multiply by the 60 and multiply by the 24 because they don't know where the units are. So you want to clearly set these things up so you can see where things should be and do the math correctly. All right, lay it up there.